It's important to properly dispose of unwanted medication or sharps. MedProject offers free and convenient disposal options near you. To learn more, call 844-MedProject or visit medproject.org.
It's Superstart Battery Month at O'Reilly Auto Parts. Get up to a $25 gift card after rebate with the purchase of select Superstart batteries. Our professional parts people will test your old battery for free and recommend the right battery for your vehicle. For power, performance, and reliability, choose Superstart batteries only at O'Reilly Auto Parts.
O'Reilly Auto Parts.
Hi there, thanks for joining us on the latest edition of Space Nuts episode 351, which is close to my heart because I used to be a Ford 351 fan back in the day when they raced around Bathurst. On today's episode, we will be looking at experimenting with wormholes and other quantum stuff that's way too hard for my brain to decipher. And we'll be upgrading SLS rockets. They asked Fred and I to do it, and I brought a pen, and that should help. Other than that, we'll be answering some questions. Paul is a follow-up question from last week, or as a follow-up answer to Paul's question from last week about black holes. Buddy wants to know about dark energy, and Dave is looking at the Huntsman, not the spider. My son found a big one in his bedroom the other day, about as big as your hand. Huntsman spiders are huge. No, this is the telescope. We'll talk about that and much, much more today on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to unravel all of that stuff, particularly wormholes, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's so good to see you today through this wormhole of broadcasting.
Yes, through the fibre optic system that is the National Broadband Network.
Yes, that's right. Yeah.
That's how we get together. I don't know what they call it in other countries. They probably call it better. But anyway...
Don't knock it. It's doing okay. So
it's working very hard though. Yes, we've managed until now. But I think the problem with NBN services in Australia and probably other services around the world is that they build them and then the demand just gets too big for what they've built, and they have to keep trying to expand it, and it's just not that easy. Which I think there are limitations to how much bandwidth can fit into the tube, and that's always the struggle, isn't it?
Indeed.
Yes. What's going on in your life, Fred, since I saw you last? Shouldn't take long to tell me.
A lot of space nutting. And a lot of panicking because of a forthcoming trip.
Oh, yeah. Oh, yeah. But that's what happens. And Judy and I have got a forthcoming trip or a fifth coming trip.
Yeah.
And we just never get the weather right when we go away. We never get it right. Yeah. So anyway, we will manage.
We think we might not either because there's a cyclone where we're going.
Oh, yeah. Well, that'll do it. That'll do it.
Yeah.
Okay, let us get started, and we're going to begin with something very complicated that you have managed to decipher and solved, and you can write your paper and win a Nobel Prize. It's all about experimenting with wormholes and quantum breakthroughs.
It is. It's such an interesting piece of work, pieces of work, because there's quite a lot of research that's going on in this field, which we haven't really talked about before. We've certainly talked about wormholes in space.
Well, we get questions about them,
and we get questions about them because they're beloved of science fiction writers as a way of getting from one bit of the universe to the other without going through the intervening.
I used one in my book, Parallax.
Yes.
You've been flogging your book for the last 5 weeks. I thought I'd throw one in there.
6 weeks now, isn't it?
I don't know.
Could be 7 if I mention it again.
No, it's not Parallax. It's the Turanian Enigma. Oh, gosh, I got the wrong book.
You're not the first person to do that.
Got the wrong book.
Yeah, actually, there's a. Oh gosh, probably shouldn't go on about this, but in the early history of the telescope, there's some, and I Giovanni Battista della Porta, his name was. He wrote a book in the middle of the 16th century. And later on, when the telescope was invented, somebody wrote to him and said, "What do you think about this?" And he said, "Oh, I wrote about that 20 years ago in my book." And he gave the title of his book, but he actually got the wrong book. So it's not just you that's not just you that does it. Yeah.
Well, maybe both have got references to wormholes, but the Turanian enigma it's much more obvious.
And very useful, I hope, in the narrative and the plot.
Oh, essential.
Yes,
essential.
So what we've got, so wormholes are a theoretical prediction of general relativity, the theory of gravity that Mr. Einstein developed in 1915 and spent the rest of his life kind of thinking about and trying to reconcile with quantum mechanics, which sort of emerged around about the same time as relativity, a little bit later. But the two, quantum mechanics says that weird things happen on very small scales, like things can be in two places at once or in two different states at once. So two completely incompatible sets of information. And Einstein spent most of the rest of his life after 1915. He died in, was it 1955? I think that's correct.
Right.
And spent most of the rest of his life trying to reconcile quantum physics and relativity. And that quest still goes on. But we now have a new tool in this game, Andrew, which is still in its infancy, but it is the developing world of quantum computers. And quantum computers, it seems, can come to the aid of people trying to undergo this reconciliation. And in particular, they are looking at the relativistic phenomenon of the potential of wormholes. We've never found a wormhole, by the way, in space.
No.
Tunnels through the fabric of space-time, which relativity predicts, but we've never found one. It's actually it's 1935 that Albert Einstein and Nathan Rosen described the first idea of wormholes. Now, there's some work that had its origins in two very, very well-known and able physicists back in 2013, work done by Juan Maldacena and Leonard Susskind, who published stuff where they speculated that wormholes are equivalent to quantum entanglement. Now, we've talked about entanglement many times as well, where you take two entangled particles, move a long way apart, do something to one, and something happens to the other one immediately. And that's so in a sense, you can see the link there, because you're talking about things that can somehow bypass our normal ideas of space and time.
Yeah.
So this has been carried on, and we now have some work done in Caltech, which actually essentially, and I'm quoting here from our good friend phys.org, this work explores the equivalence of wormholes with quantum teleportation. And so a lot of this stuff comes from Caltech. There's also a British component to this research too, which I'll get to in a minute. But the theoretical framework of wormholes being equivalent to quantum teleportation is the foundation of this work, as I said, laid down by Caltech, that actually suggests that you could do experiments in quantum computers that might be equivalent to a wormhole, if I can put it that way.
Okay.
And so that takes us now, this was work that was published, what I've just described was published back in November last year, but there has been some more work produced because a quantum, I don't know what you call it, it's an experimental setup, has been carried out at the University of Bristol in the United Kingdom. They're in the quantum engineering technology labs. It's extraordinary. It's an extraordinary world, the world of quantum computing, because there's so much happening, and it clearly impacts on our world of the big stuff in the universe. When you start thinking about the equivalents of entanglement. Sorry, let me get it right. Entanglement and wormholes. And so I'm going to go back to another phys.org article. And once again, you can find these on the phys.org website, which always gives references to the original papers. I have to say, I've looked several times at this stuff, and I'm still not sure that I understand it. But the University of Bristol has actually, one of the physicists working there, Hatim Salih, who's an honorary research fellow at that quantum engineering technology lab, has talked about counterportation, and it's a way of building a quantum computer that essentially creates a wormhole that will actually bridge space. So this is remarkable stuff. This thing's basically a simulation of a wormhole on a computer. That has been done before, but this takes it a step further, because they are working to actually demonstrate that you can, within a quantum computer, you can bypass space and time. In other words, you simulate a wormhole. And what they're saying about this is not that it's ever going to take us to different bits of the universe, because this is all happening inside a computer. But what it might well do is actually allow us to unpick the probably, and I think I mentioned this in last week's show, the underlying reality that is something more basic than quantum physics or general relativity. There's some nice quotes, if I may, from Dr. Hatim, who actually is Dr. Salih. Hatim Salih is his name. He says,
not much.
No, I'm looking for the bit I want to read. Okay, this work. The goal in the near future. This is the bit I've tried to read. Sorry, I'm flitting all through the article. The goal in the near future is to physically build such a wormhole in the lab, which can then be used as a test bed for rival physical theories, even ones of quantum gravity. So the work will be in the spirit of the multi-billion ventures that exist to witness new physical phenomena, like the Laser Interferometer Gravitational Wave Observatory, LIGO, and the European Organisation for Nuclear Research, CERN, with the Large Hadron Collider, but at a fraction of the resources. In other words, we're doing it on the cheap. I love that. Our hope is to ultimately provide remote access to local wormholes for physicists, physics hobbyists and enthusiasts. Thank you very much.
Coffee time.
Yes, it's coffee time. And to explore fundamental questions about the universe, including, here we go, the existence of higher dimensions. So it's all about really poking into this hidden world that we think unifies relativity and quantum physics, and about which at the moment we know very little.
Yeah, and it's fascinating science, because we've talked in the past about trying to reach the speed of light to get somewhere in space faster than we're capable of now, but the energy required makes that impossible.
Yep.
But if we were to perfect this kind of science and do it on a large scale, do you foresee a day where we might be able to create wormholes to move across vast distances in space instantly, like they do in science fiction?
No.
Okay, good answer. And the other thing I found interesting in this article was how they describe Google's involvement in this.
That's right. With Google is heavily involved in quantum computer research. Now, the reason I said no, Andrew, is that, and it may be the wrong answer, if you can do it with bits of information, which is really what this is all about. It's about qubits, which are the information bits in a quantum computer. It's about sending them from one place to another, because information is, in many ways, is reality. And in fact, some physicists actually think that information really underlies it. That when we start really digging into the unifying links between relativity and quantum physics, we might find that information is actually the common ground. So it's one thing to send qubits through a wormhole. It's quite another to send a spacecraft full of people through one, which certainly in relativistic terms needs you to warp space-time to such an extent that you need almost the total energy budget of the universe to do it.
So still the same problem.
Yeah, it's the same problem, that's right.
Yeah.
But watch this space.
I was going to say the other problem is that based on what I've read briefly, what comes out the other end is a duplicate of what went in. So it's, you send people through a wormhole in space, it's not going to be them coming out the other end. It'll be their carbon copies.
Yes.
Not quite as good either.
It will be a carbon copy, but I think in the process the original gets destroyed. Is that not right with that? Yeah.
That's what I read, yeah.
Yeah.
So probably not a good plan.
No. No, that's right. No, I think information's fine. Humans, maybe not so fine.
No, definitely not. Yes, if you'd like to read up on that story, most certainly go to the phys.org website, PHYS. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Well, hi everybody, it's Steve from Down Under here. I wanted to let you know that today's episode of Space Nuts is brought to you by Curiosity Stream, the streaming service perfect for people who want to know more. With exclusive award-winning films and shows, Curiosity Stream has the deepest collection of top-quality documentaries from around the world. Now, Andrew and I can tell you that in our household growing up, Mum and Dad didn't care what we were watching on TV so long as we were watching documentaries, and I wish we had Curiosity Stream back then. Now, whether you're interested in science, history, nature, technology, travel or more, Curiosity Stream has something for you. And with new content added every week, you'll never run out of things to watch. It's a big favourite in our household, and I know it will be in yours too. Curiosity Stream is available on all your favourite streaming devices, including Roku, Xbox, smart TVs, Apple TV, Amazon Fire and more. Plus you can watch it on the web and on all your mobile devices. Best of all, it's available worldwide, so you can explore the world's top documentaries no matter where you are. So why wait? Go to curiositystream.com/space nuts for unlimited access to the world's top documentaries and non-fiction series. And for our fans here at Space Nuts, use the promo code Space Nuts and save 25% off your subscription, of course. There is really something for everyone on Curiosity Stream. So click the link in the show notes or go to curiositystream.com/space nuts and save 25% right now. Enjoy the world's best documentaries, just like Andrew and I did growing up with Curiosity Stream these days. And now it's back to Andrew and Fred with Space Nuts.
Houston, Tranquility Base here. The Eagle has landed.
You're listening to Space Nuts, the podcast about astronomy and space science with Andrew Dunkley and Professor Fred Watson.
It's good that we had a little NASA link there because we are going to now talk about one of the most amazing pieces of hardware that NASA has developed, and that is the Space Launch System, the SLS rockets, which have been around for a while, but they're still proving to be incredible workhorses. And now they're looking at an upgrade.
That's right. So it's the rocket motors themselves that we're talking about here.
Yeah.
And, excuse me, we discussed this last November, when Artemis 1 was being launched on the first flight of the new SLS, the Space Launch System, NASA's SLS system. It's still the world's most powerful rocket. It might not be for long, but it still is. And so the engines of the Space Launch System's core, if you remember, it's got a sort of standard rocket body core, but two huge boosters bolted on the sides. And those boosters are effectively the they're derived from the boosters that used to be used with the space shuttle.
Yeah.
They're chemical solid fuel rockets. You light the fuse and off it goes. And in fact, on launch, they provide, together, they provide something like 80%. No, something like 75% of the thrust. The rest of it comes from these RS-25 engines, which were developed for the space shuttle. These engines were first certified in 1979, Andrew. So this
Wow.
is, excuse me, stuff that goes back a long way.
Yes.
Followed 2 years later by the first space shuttle launch, which used them. So they are really quite incredible machines. 500,000 pounds of thrust each, if I am reading my figures correctly. That's right. So 500,000 pounds of maximum thrust each. And they are, of course, they're controllable, they're throttleable. So you can actually, once you've thrown off the boosters, which just, you light them and they just go, you can control what the spacecraft is doing. There were 3 of them in each space shuttle. There are 4 of them on each Space Launch System core. There's some really quite extraordinary facts. NASA have produced, as they do so well, some fact sheets about these engines. So 135 launches in the 30 years of space shuttle launches. A lot of adaptation work that's gone on, and they've started off the SLS, the Space Launch System, with 16 of these RS-25 engines. So that would be enough for 4 launches, because unlike the space shuttle, which came back to Earth at the end of every flight, the SLS gets dumped in the Atlantic, so it doesn't come back. But now what's happening is, back in, I think, 2017, the company that built them, which is Rocketdyne, effectively, it's actually Aerojet Rocketdyne now. They used to be just Rocketdyne. Aerojet Rocketdyne, they started up again to build their new engines back in 2017, and they've got a contract now to build 18 of them. So these engines are actually the new shiny version of the RS-25 with the thrust upgraded, 111% more than it originally was in 1979. Sorry, yes, so, but 10%, sorry, 11% more. It's quite an amazing thing. One fact that I loved about these engines, Andrew, is that the gases that are coming out of the exhaust when it's full thrust are traveling at 13 times the speed of sound.
Wow.
Which is why you get that, it's a sonic boom that you're getting when you stand and watch a launch and sort of feel the vibration, which I've never done. But yeah, quite extraordinary.
I love the way they crackle, these engines.
Yeah, they do, don't they? And that might be that might be it. That might be the sonic booms, basically doing exactly that.
I guess we're going to see these things in action for some time to come. They recently announced the crew for the Artemis mission that's going to go around the moon with humans in it.
Yep.
There's a lot of milestones being met there. But these engines are just going to keep on keeping on until they can come up with something better. And I guess time will be a factor in that. But they're just so powerful. Do we at this stage need anything better, especially given these are being upgraded? So I suppose it depends what we're going to send up there. If we're going to need to put heavier payloads into space and things like that.
It's
if we're going to build interstellar spacecraft, we'll probably need some heavy lifting to be done.
That's correct. We will. So it kind of highlights the difference in philosophy. If you think about the SpaceX's ventures in this game, the Starship Heavy, which is very near to having test launches, and that's works on the same philosophy as SpaceX has used for their Falcon rockets, where you have a relatively small number of engines. If I remember rightly, they're the Raptor engines. I think I'm right in saying that. You have smallish engines, but you put lots of them in. So I can't remember how many rocket motors a Falcon 9 has. It may even be 9. It's quite a lot, but it's many, many more in the Starship. It's probably 20 or 30 of these things all firing together.
Yeah.
Whereas the philosophy that's been adopted by NASA is, and it actually, this highlights another contrast, which I'll get to in a minute, but it's to use bigger engines, which are probably much more high tech. These are, I think, if I remember rightly, I think they're called staged combustion engines. They're a particular type, which actually it gives them this extraordinary power. And they, each one of these engines is about the size of 2 cars, one piled on top of the other. They're huge things.
They're massive.
And you've got 4 of them on the space shuttle. So, on the space launch system. So, it's a different philosophy. What I was going to say was, it harks back to the 1960s, Andrew, when, Saturn V had engines which were very similar to these.
Yeah.
And 5 of them on the first stage.
Yeah, I've stood under one at Cape Canaveral.
Yeah, that must be quite awe-inspiring. That's right.
You see it on TV and you think that is enormous, and then you go and you know how TV makes things look bigger.
Yes,
the Saturn V is an exception.
It's even bigger.
When you see it, you go, I was going to swear, holy cow!
Yeah, that's the word.
Yeah, it is. It is staggeringly huge. They've got it hanging from the roof in a Saturn V exhibition centre at NASA, and it fills the whole place up. And they've got the stages broken up, so I started at the back and moved forward. But you could stand inside one of those exhausts, and you still wouldn't be able to reach up and touch the top.
No, that's
humongous.
Right. Yeah.
Very, very exciting to have been able to do that quite a few years ago now. But if you're ever around Cape Canaveral, Florida, do it. You've got to do it. It's just so brilliant.
Hopefully, I'll be doing it next year because we're running a tour there.
Exciting.
Yes, but what I was going to say, so the 5 big engines of the Saturn V contrasts with the Soviet Union's equivalent at that time, which you and I have spoken about before, because they were building their own version of a Saturn V, quite different in shape and structure. That was the N1, it was called. That's the Soviet Union's N1 rocket, which had, I think, 32 smaller rocket motors.
Yeah.
In its first
didn't they blow up a lot?
They never managed to get one to fly successfully. No, that's right. And it certainly nobody ever got him one. I think there were 4 test launches and they were all, none of them really succeeded. And one of the problems I think that they found was, when you've got lots and lots of smaller engines, you've got the sort of interplay of vibrations between them. It's not just the vibration of one engine or a small number of engines shuddering through the rocket. It's all these things competing with one another in vibrations. And if you get resonances, things where vibrations build up.
Harmonic disturbance.
Yeah, that's right. The sort of same thing that happens with sound.
The Tacoma Rapids Bridge.
Yes, exactly.
Was a harmonic disturbance.
Yeah, that's right. So that's the sort of thing that would destroy a rocket. And maybe one reason why the Soviet Union's N1 was never successful.
Well, that was also the demise of the Comet aircraft. I think it was the Comet passenger plane.
Yes,
which threatened Boeing for many years until they had a few inexplicable crashes. It turned out to be metal fatigue caused by those vibrations.
No, it was the square windows.
Square windows.
I remember all this really well.
I saw a doco about it.
Yeah. Well, I saw it.
Wow.
Yeah. So you're absolutely right. It was the world's first turbojet aircraft, a passenger aircraft. and did threaten to give Boeing a run for its money. There were design differences. The Comet had 4 engines which were actually built into the wings. And of course, Boeing went the other way, had them slung under the wings, which turns out to be a much, much better idea on all kinds of different counts. But what essentially scuppered the Comet, they had, I think, 3, maybe 4 accidents where the aircraft was lost. It was traced to be due to sudden decompression of the fuselage, and it was because of metal fatigue in the corners of these square windows. Yeah. The windows were square.
I knew metal fatigue came into it somewhere.
That's right. You were right there. And I mean, maybe vibration had an impact, but it was the fact that the square corners of these windows were a critical point of failure, and that's where the metal fatigue set in. And in fact, it led to rapid depressurization, and many lives were lost. And of course, it scuppered the British aircraft industry. They were built by de Havilland, which was one of many British aviation companies post-war, all of which wound up being part of British aerospace, which is
amazing.
Now, nothing like Boeing in terms of scale.
No. Well, that explains why all aircraft windows are essentially round now,
or
have round corners.
That's right, absolutely right.
And to answer one final point, there are 27 engines on the Falcon Heavy.
There you go. Okay, I wasn't far off. Yeah,
exactly. Yeah, but that's really interesting. It'll be quite exciting to watch the future of rockets and rocket science with the RS-25's continued development. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, let's go to our Q&A section, and we've got a follow-up from last week. Paul messaged us. Paul's from Melbourne, Victoria. I'll repeat his question because you've done a bit of research on this. There's been talk recently about the energy that causes the universe to expand coming from black holes. If this is so, then wouldn't we see the time-space around or near a black hole expanding at a faster rate than further away from black holes, for example, between galaxies, or that in between in spaces between filaments of the cosmic web? Wouldn't the filaments of the cosmic web be expanding faster? And we tried to answer, but we thought it deserved a little bit more homework.
I couldn't remember the link that had been made between black holes and dark energy.
Yeah.
And what it is, and there's a very nice article on space.com entitled "Black Holes May Be the Source of Mysterious Dark Energy" by Stephanie Waldeck. And it kind of explains where this research is going. But unless you're sort of into the mathematics of the original research, you probably still feel, as I do, that there are questions remaining. So, by the way, it was this research was published in the Astrophysical Journal Letters on February 15th, as I think you mentioned last week when we were talking about it, Andrew. So the research in question has looked at the mass of supermassive black holes through the history of the universe. So remember that we think all galaxies have a supermassive black hole at their center.
Yep.
You can, by using the trick of look-back time, you can investigate these black holes as you look backwards in time. And it turns out, and this was the work, it's actually led by the scientists at the University of Hawaii at Manoa in Honolulu. They've looked back over time, and what they found is that the black holes sort of early in the universe, they are more massive than they ought to be if all they're doing is accreting stars. That's how we think supermassive black holes grow, by gobbling up stars and other debris, gas stars, dark matter probably, that makes them acquire mass. But this imbalance in the mass of black holes that suggests that they're more massive than they should be if all they're doing is chewing up matter has led these scientists to believe that the sort of missing, if I can put it this way, the missing mass in the black holes is actually dark energy. So let me read, as I often do, a quote from one of the authors of this study. And actually that space.com page that I mentioned has got a couple of very nice videos about this stuff. But Duncan Farrar, who's at the University of Hawaii, he says, we're really saying two things at once. That there's evidence that the typical black hole solutions, and by that he means what the theory of relativity tells you, don't work for you on a long, long time scale. And we have the first proposed astrophysical source for dark energy. In other words, they think that black holes have something to do with dark energy. Now, I think what I said a few minutes ago, I think I said it the wrong way around. Because I think I said the younger galaxies have more than they should have, but it's actually the other way around. It's the older galaxies. They're bigger than they should be, right? If all they've got is stars that they're gobbling up. And so now the link between that, a sort of kind of dark energy component within black holes, and the dark energy in the universe is the one that I am still struggling with, because I'm not actually sure how you get from one to the other. And the reason is the black holes are discrete objects. They are objects in space. Dark energy, as according to our best understanding, is the same everywhere. It's not in blobs. And that was the thrust, I think, of Paul's question. Why don't we see distortion of space around black holes? Well, we do, but why don't we see more than we should with this dark energy, if dark energy is something to do with black holes? And I don't really see the link. I think it comes out in the mathematics. I probably ought to have another look at that paper, which is right in front of me now, and it is entitled Observational Evidence for Cosmological Coupling of Black Holes and Its Implication for an Astrophysical Source of Dark Energy.
Right.
And it's got a lot of big words in it and some big equations. Actually, it's not too bad for equations. It's not as bad as I remembered. It's an interesting paper. I will read it again. It's the sort of thing you really have to dedicate a day to sit down. There's a large list of authors. Duncan Farrar is the lead author from the University of Hawaii. But yeah, if you have a mathematical bent, I'm addressing now our listeners because I know you don't, Andrew, but that's a paper to read and have a look at.
So the basic answer to Paul's inquiry is that dark energy is even throughout the universe, therefore the effects he's describing wouldn't occur.
That's correct.
Okay.
I think that's a beautiful summary. I wish I'd said that.
Did that without an equation.
Of course, there is an equation that links all this together, and that's E equals mc squared, because
yes, of
that's
course.
the one that tells you that energy and mass are equivalent.
Yeah.
Yeah.
Thank you, Paul, again, and I'm glad we could follow that up and fill in some of the blanks. Let's now go to Oregon. It's our good friend, Buddy.
Hello, Space Nuts. Buddy from Ontario, Oregon. Hey, since they think dark energy is coming from black holes, why aren't they losing more mass if the energy is being redistributed out into the universe? Are they... I don't get it. Could that possibly be what's pushing our solar system back, our galaxy back together, keeping it from falling apart? Is that we're losing energy in the local area and it's being redistributed over the entire universe? And so we're only getting a little piece of that energy back in our piece of the universe. So it's kind of pushing in. Just a thought, guys. Hopefully Fred can get my head straight on this one. Keep up the good work.
It kind of relates to Paul's question, but
it does.
I just thought it was a good question because it is the one that's got a lot of people scratching their heads at the moment,
me included.
Yeah.
So no, but what Buddy says is exactly right. But in fact, the observation is the opposite of what he said. He said, "Why aren't they losing mass?" And the observation is that they're fatter than they ought to be. They've got more mass, which is being interpreted as dark energy. But it's the trick of getting that stuff out of the black hole and into the wider universe that is the missing link in my understanding of this issue. So, Buddy, you and Paul together are raising questions that are basically the same as the ones I've got. I will once again have a look at this paper in the Astrophysical Journal Letters, and if I can see the breakthrough, we'll raise it again because it is such an interesting topic.
It is,
especially if it does solve the problem. And I'm sure there must be other scientists working on this. That paper was published back in February. I'm not sufficiently close to the gossip within the cosmology community to know what the story is. But in fact, my one of my links into that world is currently on sabbatical in Oxford, so I can't ask him very easily. Yes, we will see as time goes on, and no doubt this will crop up again in Space Nuts. So watch this space. That's the best I can do. Thanks again, Buddy and Paul, for your questions.
Yes, and I suppose when you're talking about relatively new science, it's always going to spawn questions. And at the moment, we don't have an absolute definitive answer. We're still trying to figure it out. And that's where, people send us questions and say, well, what's a white hole? Well, we don't know. We've never seen one, don't even know if they exist. So it's the same with dark energy, dark matter. We know they exist. We don't know very much at all about dark energy. We've got a bit more of an idea about dark matter. But again, they are still puzzles to be solved, I would venture to say. Thank you, Buddy. Thank you, Paul. Sorry, go on.
No, I'm reading through the abstract of that paper again. So there's a crucial sentence in here which says the continuity equation then requires that black holes contribute cosmology as vacuum energy. So there you go.
All right. I understood that.
Yeah. Yes. Yeah.
Fair enough. Thanks, Buddy. Thanks, Paul. One final question before we wrap up this episode comes from Dave in Colorado. Hi, Andrew and Fred. I found your podcast about a year ago, and I've gone back and listened to every episode. Are you still married? I love the podcast and can't wait for the next one to come out each week. The question I have is about the Huntsman Telescope at Siding Spring Observatory. I was watching an Instagram short about it, and I saw Professor Fred's name on a plaque on the outside of the dome it resides in. I was wondering if you could explain what science the telescope is doing, since it's such a unique telescope, or a group of telescopes technically. I've tried to find out what it does and can't seem to find out much about it. Thanks for your work. Thanks for the work you do, and keep this podcast going and growing, Dave. It's called the Huntsman Telescope because it doesn't do very much, but it's really good at killing huntsman spiders.
Yeah, probably.
Bang them over the head with it.
Oh, if you do that, yeah, you would. It's quite heavy. So it is unique. Dave's right. It's a telescope that uses 10 commercially available telephoto lenses. They're very high-end telephoto lenses. They're Canon lenses made principally for sports photography. So, when you watch a football game or something like that, you see these guys with these long lenses sometimes on tripods, sitting by the ground. They're the ones that they're using, that kind of lens. But it turns out this is work that was probably kicked off, I think, by a colleague of mine at Macquarie University here in Sydney, Dr. Lee Spittler. In fact, I think he's Associate Professor Lee Spittler now, if I remember rightly, which is very, very well deserved. They have used these lenses to the thing that makes these lenses special is that they've got very low scattering characteristics. In other words, you send light through a normal mirror lens, which is probably what you'd want to use, and you got not just the reflection, but you get light scattering. And what that does is if you form an image on a very sensitive electronic detector, you're spreading scattered light all over the image. And that means that the very faintest objects that you might want to look at, including sort of wispy tendrils of stars in distant galaxies, they're swamped by the scattered light from the brighter bits of those distant galaxies. So what you want is a lens that will have very minimal scattering characteristics. In fact, I know that Lee took his idea for this telescope from something, I think in the US, called the Dragonfly telephoto array. And Huntsman is a telephoto array. It uses 10 of these lenses. And the sorts of research that it's involved with is stuff that needs you to look at very faint extended objects. And by an extended object, I mean something different from a point source. Now, Andrew, you might be surprised, as I was decades and decades ago, to know that the sensitivity of a telescope to an extended object, something like a nebula rather than a point source, doesn't depend on the diameter of the telescope. It's actually a function of the focal ratio, which is something well known to photographers. The faster the focal ratio, in other words, the smaller the F number, if I can put it that way, the more sensitive you are to extended objects. It doesn't matter how big your lens is. Which is kind of counterintuitive. But that, of course, explains why astrophotographers, your hobby astrophotographers these days, can produce images of the universe that rival the ones David Malin was producing with the Anglo-Australian telescope 30 years ago. It's because of the focal ratio dependence of extended objects. It's fabulous stuff, and it's great science. So Huntsman's really good at things where you've got very faint extended objects. And I'm reading now from the Huntsman website the sorts of questions that it will help to answer are about galaxy formation and evolution, including star disk formation, galaxy growth through the coming together of satellite galaxies, understanding gas turbulence in the galactic interstellar medium, understanding the relationship between star gas assembly and cold neutral hydrogen gas assembly, and it's also got a role in looking for exoplanets as well. The number of long period exoplanets around test stellar systems is another of their declared interests. It's a great telescope, Dave. And I was very honoured to be asked to open it last year.
Hence the plaque, Dave.
Hence the plaque. Yeah.
Thank you, Dave, and I hope that helps you understand a bit more about what the Huntsman's going to do. The only major inaccuracy, you said it had 10 cameras? 10 lenses?
10, yes. It's
a Huntsman spider only has 8 eyes.
It does, I know. This one has 10 eyes, so it's a super Huntsman.
It's a super Huntsman.
And one of its other advantage is that by strapping on more lenses, you can make it into a super-duper Huntsman.
Yeah.
And I think there are plans afoot to try and increase the number. But yes, it's 10 lenses at the moment.
Awesome. Thank you, Dave. Thank you, everyone who sent in questions. Keep them coming because we love to hear from you. You can do that via our website, spacenutspodcast.com or spacenuts.io. That's for younger people. And just click on the links. There's a link called AMA where you can send audio and text questions, or just hit the tab on the right-hand side of the homepage. Send us your voice message. If you've got a device with a microphone, that's all you need. Tell us who you are, where you're from, and ask your question, and we will do our best to put it in there. We get a lot of questions that are almost the same, so we tend to not run them all, but we did today with Paul and Buddy. They were basically talking about the same thing, but it fitted in with the discussion. But please send us your questions by all means. And if you thought about it and never got around to it, we'd love to hear from you, especially if you're a newbie. We haven't had too many newbies lately, but we get them occasionally, and that's nice. We'd love to hear from everybody all over the world. And while you're on the website, don't forget to check out the shop, because Fred's got books in there.
which I'm not going to mention
at all. And there's the
no.
Astronomy Daily newsletter, and if you want to find out about how to support Space Nuts, there's a little link there as well if you're interested. Okay, Fred, that wraps it up for another week. Thank you so very much.
It's always a pleasure, Andrew, and we'll talk again soon.
We will indeed. Professor Fred Watson, astronomer at large, and back to Hugh in the studio. Yep, the usual response. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.